All right, here we are in the third week of the course, and this is where things are going to start to become a little bit more interesting. So let's get into it. Quite a bit of a busy agenda for today, so I'll give a little bit of a recap of what we have learned already about regression analysis, specifically the simple linear regression model, which we talked about a lot. And then we'll move into new theory. I want to start with first discussing a little bit the relationship between regression analysis and correlational analysis, or correlation coefficients and regression coefficients, because they are quite closely related to each other. And then we'll go further on the topic of regression analysis by discussing so-called multiple regression analysis, where you will have more than one independent variable in your regression model. We'll talk a little bit about how to compare different regression models with different sets of variables included. We'll discuss how to interpret the coefficients of multiple regression models, and we'll make a start with discussing some issues that you have to start to consider, specifically when you deal with models with multiple independent variables. So we'll talk a little bit about sample size and multicollinearity issues that you have to consider then. But first, let's start off with a little bit of a recap, what we already know. So we discussed the simple linear regression model, which has the general form of yi equals b0 plus b1 xi plus an error term, where you say, well, the value of the dependent variable y for each case I is equal to a constant value or an intercept, which is the same for all the cases, plus a regression coefficient b1 for our x variable, for our independent variable, multiplied by the value on that independent variable x for each case I in our data set. And because we recognize that we won't ever be able to perfectly predict the outcome, the dependent variable y for each case, we also include an error term that captures the difference between what we would predict based on the regression coefficients for our dependent variable and what we actually observe for the different cases for our dependent variable. So we already know how to find the right values for b0 and b1. So finding those values is sometimes called estimating the model. And the way to estimate these kinds of simple linear regression models is the OLS method, or ordinary least squares, which now we even did in the LB lecture from last week by hand. So you saw there's no magic going on. It's something that we could actually do ourselves if SPSS would stop working altogether. So ordinary least squares estimation, the idea of finding the right values for b0 and b1 by minimizing the sum of squared residuals. So basically finding the best fitting regression line for our observations. We discussed the interpretation of the regression coefficient for our independent variable x, so the b1 coefficient, and we discussed how we can interpret this as an estimate of the effect of x on our predicted value on the dependent variable based on the sample that we have observed. Yeah, so whenever you interpret these coefficients, you should be aware that they are always, represent effects of x and y, expressed in predicted values of your dependent variable, of your y variable. So that's how to generally interpret those regression coefficients, but of course that's just what we can say based on our sample. Usually we don't care just about the sample, we want to use that sample to make some kind of generalizable statement about the population, in this case some statement about the effect of x on y of the independent variable on the predicted value of the dependent variable in the population. So how can we do that? Well, we can do the classical statistical hypothesis test. So we can test hypotheses about values of the coefficient in the population, and we can test those with a t-test. So these will be hypotheses where you have a null hypothesis and some alternative hypothesis, and usually the null hypothesis will be that the effect of the independent variable on the dependent variable in the population is in fact zero, so there is no effect at all, which is the same thing as assuming that the p coefficient in the population would be exactly zero, and then seeing whether we can reject that null hypothesis in favor of an alternative hypothesis that could be that it is not zero, or that could even be a directed hypothesis that is larger or smaller than zero, so that's a positive or a negative effect. And the way to do that is with a t-test, because under the assumption that the null hypothesis is true, so under the assumption that in the population, in fact, our independent variable has no effect on the dependent variable at all, we know that the coefficient that we find in our sample divided by the standard error that we find in our sample, so in other words, the t-value, is going to follow a t-distribution. And so we can use that t-value to see, well, how far out in the tail of the t-distribution are we? And in other words, then find the corresponding p-value, the probability value of finding this t-value or a larger t-value, if it is in fact true that in the population the effect of x and y is exactly zero, so that the population coefficient is exactly the value 0, that there is no effect whatsoever. We can also say something about, well, our error term. And what is our error term? Well, if we are talking about a sample, then we refer to this error term as the residual, and it basically captures that variation in our dependent variable that is not associated with our independent variable. So variation we usually express as variance in statistics. So basically our error term tells us something about what the variance that we are not able to explain with our independent variable x. So those differences among the cases that are not associated with differences on the independent variable x. And we can even see, well, if we think about the total variation that we start out with in our dependent variable, so the variance that we have, how much of that is being explained by the independent variable that we included in the model. And this is what the R-square value, the coefficient of determination, comes in as a measure of goodness of fit of our model fit, because R-square is the proportion of explained variance in our sample. Yeah, so we can say in our sample, R-square represents the proportion of the total variance in our dependent variable that is explained by differences in our independent variable. And if you multiply that by 100, you can express it as a percentage. So that would be the percentage of explained variance by our independent variable in our dependent variable. But of course, again, this is based on the sample that we observe. So if you also want to say something about, well, the goodness of fit of our model, if we would have done that for the fitted the model for the entire population, which is usually what we want to say something about, then we have already seen that we can also test statistical hypothesis about the R-square value in the population. So again, we can have a null hypothesis that R-square is 0, that if we would fit our regression model with all the observations in the entire population, then we would be able to explain no variation whatsoever, 0, so the R-square would be 0 in the population. And we can test that null hypothesis against the alternative hypothesis that it is going to be larger than 0. That's a positive value, can't ever be a negative value, because we're talking about explained variance. Variances can't be negative, and we can't explain less than nothing. So it always has to be some positive value or 0. So we can test the null hypothesis that it is exactly 0 in the population, so we are not able to explain any variation whatsoever with our independent variable, against the alternative hypothesis that it is a positive value that is larger than 0 in the population. And the way we do that is through an f-test. So we can use that f-test to say something about, well, how likely is it that we find the R-square value that we find with our sample, and so to calculate the corresponding f statistic that can be calculated from that. We saw how to do that. Say, well, how likely is it that I find this f statistic or a larger f statistic under the assumption that is in fact true in the population, that we are not able to explain any variation whatsoever. So under the assumption that R-square is exactly 0 in the population. And again, there we can use the f distribution, look how far out in the tail of that f distribution are we with that f value. That will tell us something about the probability of this, about this probability value, this p-value. Okay, so that's what we already hopefully know by now. Now, before I start going into more things that we don't know, the multiple regression model, I first want to briefly touch on something else, because it's going to come in very, very useful already today with this lecture, but also later in the course. And that is the relationship between regression analysis and correlation coefficients. Because you will have heard about both in the past. You will probably have heard a lot about the correlation coefficient. Yeah, so Pearson's product moment correlation coefficient. And I just want to show you what the relationship is between the two. And before I can do that, I want to start very, very, very basically, before we even talk about what is a correlation coefficient, talk about something that's even more basic, and that's the idea of a Z-score or a standard score, something in which you will have learned about a lot in your previous statistics courses, and probably in the context of, well, if you want to compare different values that are measured on different scales and you somehow want to make the measurement comparable, you can standardize those variables, and you do that by basically calculating these so-called Z-scores or standard scores, and they express the number of standard deviations a specific observation is removed from the mean. So for each observation in our data, we can calculate this Z-score, this standard score, and it will tell us how far removed that observation is from the mean on the scale of standard deviations. So how many standard deviations above or below the mean is this specific observation? So just a refresher, how do we calculate a Z-score? So a Z-score for a specific case I is the observation for that case I on some variable x minus the average, the mean value on that variable x that we observe in our sample, divided by s divided by the standard deviation. So you can see again with this formula that it nicely expresses exactly what the interpretation is of a Z-score. The top part of the formula tells you that it is something about how far removed is an observation from the mean value of that variable. And the bottom part basically is how we scale that value, and we scale it in this case to standard deviations of that variable, to make it comparable. Yeah, so in this case we're dividing by the standard deviation. So we know that a Z value tells us how many standard deviations a specific observation is removed from the mean value on that specific variable. And I'm talking about Z-scores because you might have forgotten how to exactly interpret a correlation coefficient. So what is a correlation coefficient? Well, it's really, so Pearson's R correlation coefficient. That's usually, we're using the letter R, little r, to indicate Pearson's correlation coefficient. Well, it tells you about the relationship between two variables, so an X variable and a Y variable, and it does that in Z-scores. So very, very basically, it is making the assumption that there is a linear association between X and Y, so there's some kind of linear model like the ones that we have already seen in this course. It expresses the strength of that linear association, and it does that in Z-scores. So in other words, if you have a correlation coefficient, what does it tell you? Well, it tells you with how many Z-scores X changes when Y changes when X increases with one Z-score, or vice versa, because it's a symmetrical measure, so it doesn't matter which is the X and which is the Y variable. How many Z-score X changes when Y increases with one Z-score, one standard score. Yeah, so correlation coefficients are expressed in Z-scores, and that's how you can actually interpret them. So they are on a standardized scale, a Z-score scale, basically. Yeah, so you can think about this R square as this R value as well. The larger the value is, whether it's positive or negative, so the further removed from zero it is, the stronger the relationship. Meaning that if you think about this correlation coefficient as a linear relationship that you can think of as a line at 45 degrees, at a 45 degrees angle between our X and Y variable, and you think about all the individual observations around that line, then the closer all the individual observations are to that line representing the relationship, the larger the value of the Pearson's correlation coefficient. I'm saying absolute value because, of course, a correlation coefficient can be either positive or negative. So it could be either a positive relationship or a negative relationship. But the larger the absolute value, so absolute value is just forgetting about the minus, about the negative sign. The larger the absolute value, the closer the observations are to that line indicating the linear relationship between x and y. So that's basically how you can also interpret the correlation coefficient. So it means the same thing, basically. Yeah. So why am I telling you this? Because correlation and regression have a direct relationship with each other. And the best way to understand that is to think about how could we get from one to the other? How could we translate a regression into a correlation or a correlation into a regression? So how you could do that is, for instance, well, if you have two variables, an x variable, independent variable, and a y variable, a dependent variable. So until now, we just assumed that we would be working with the observations of those variables directly. So I have the x variable on whatever scale it's measured at, and the y variable on whatever scale it is measured at. Yeah, so for instance, you worked with the variable income measured in the European Social Survey, and that was on a scale of deciles. You worked with the variable satisfaction with democracy, and that was measured on a scale and on a point scale from 1 to 10 or 0 to 10, one of those. Yeah, so on the original scales. So that would be, if you just use those original variables, then we're doing a regression analysis. What we could also do is we could first take those variables and calculate z-scores for those variables. So take the z-score for the z-scores for the x variables and z-scores for the y variable. So we did this already. We already saw that. What is a z-score, standard score? It is the observation on the variable minus the average on that variable divided by the standard deviation of that variable, and that will give us the z-scores or standard scores. And we can do this for our independent variable and our dependent variable. So we could transform our original income variable into z-scores, and we could translate our satisfaction with democracy variable, for instance, into z-scores. Yeah, so looking for each individual observation, each case. First, what is the mean value on, for instance, this income variable? And then how many standard deviations is this specific observations removed from that mean? Or for the dependent variable satisfaction with democracy, what is the mean value on satisfaction with democracy? And then calculate for each specific observation how many standard deviation removed that observation is from the mean on satisfaction with democracy. So that's just transforming the raw scores into z-scores. And then we can just run a normal regression model on those transformed variables, on z, y, and zx, on the z-scored variables, right? So we could literally just create a new variable in our data set for zx and a new variable for zy, and then run the regression model like we would normally do. So we would get our basic simple linear regression model, but now for z-scores on our dependent variable. Yeah, so here we have zy and z-scores on our independent variable x. So we have zx. So now we have basically a regression model, but the variables that we are using to estimate this regression model aren't the original raw scores. They are the transformed z-scores of those variables. Well, what's going to happen? Well, one thing is, by definition, the b0, the constant, will have to be 0. And that is because we have transformed our variables into deviations from the mean. And mathematically, that means that the constant always has to be exactly 0. So we can actually just drop the b0 coefficient from our equation because it will be 0 anyway. It will be exactly 0 by definition. So we can even forget about it in our model, right? If something is 0 in our model, we can just drop it from our model. So if we would use z-scores on on dependent variable y and independent variable x, then b0, our constant, our intercept, is by definition 0, and we can just drop it from our equation. So we can rewrite the same equation as just being the z-score on our dependent variable for each case is equal to this regression coefficient multiplied by the z-score on the independent variable plus still our error term. Even more interesting, our b1 coefficient will be exactly the same as the Pearson's correlation coefficient R. In other words, a regression model and a correlation are exactly the same. The only thing that is different between them is on which scales your variables are measured. If they are in raw scores, then we're talking about a regression model. But if we would transform them into z-scores, so standardize them, then that would be the same as a correlation coefficient, right? So regression analysis and correlation analysis really is the same thing. There is no fundamental difference between the two. It's just a different way of expressing the scales of our variables, which might be a bit of a disappointment to you, because you might have gone into this course with we're going to learn all kinds of stuff about causal analysis, and you probably also have heard quite often that correlation does not equal causation. So you probably already have some kind of idea that just looking at correlation coefficients doesn't necessarily tell you a lot about the causal effects of x on y of the one variable on the other variable. And now you learn that but regression analysis is also basically just correlation, but expressed on a different scale, on an unstandardized scale, which is absolutely true. And it's also one of the reasons I'm showing you this, because one of the things that you need to learn during this course is not that our analysis magically become a causal just because we're doing a regression model. It is really about how we use it that will allow us to make stronger causal inferences. So again, we could just z-transform our variables. And as a matter of fact, we often do, and then we call it a standardized coefficient, sometimes also referred to as a beta coefficient. So again, it's the same model, it's just a different scale. If we would have standardized our variables, we would call that a standardized coefficient, because now it is expressed on the standardized scales of our independent and our dependent variable, which you don't actually even need to do yourself. SPSS automatically always does it for you. If you estimate a regression model, then we talked a lot in the previous meetings about what is here, the unstandardized coefficients. So how to interpret these unstandardized coefficients. We talked about the standard errors and the t-value and the p-value. But there is also a column we didn't yet discuss, and this is this one, the standardized coefficients or beta column. So this is where SPSS reports the standardized coefficients. So all that stuff with transforming into z-scores and then estimating the regression model again, SPSS basically automatically already does that for you. Yeah, so now we have two different coefficients here for this income effect on how satisfied are you with the national government. We have the unstandardized coefficient, which again you have to interpret on the original scales of the variable. So in this case, it's 0.167. So what does that mean? It means that for every additional decile of household income, because household income is measured in deciles in the ESS, the predicted value on satisfaction with the national government is going to increase by 0.167 points, because it's measured on a point scale. But now we also have the beta coefficient, completely different value, 0.235. How do we interpret this? Well, in this case, we interpret this as for every one standard deviation higher on household income, the predicted value on satisfaction with the national government is going to increase by 0.235 standard deviations. Yeah, so we have transformed both our independent and our dependent variable into z-scores. So now how do we interpret the standardized coefficient? Well, we interpret this as for every one standard deviation increase in the independent variable, the predicted value on the dependent variable is going to increase by that many standard deviations, that many being the value of the beta coefficient. So again, for every one standard deviation increase in household income, the predicted value on satisfaction with the national government is going to increase by 0.235 standard deviations, which is exactly identical to the correlation coefficient. You can check this for yourself, run a simple linear regression model, then do a correlation coefficient through SPSS on the same data, and you will see that those values for the correlation coefficient and the standardized coefficient in a simple linear regression model are exactly identical. Going one step further, you might have already noticed that the model summary, where we discussed already the R-square value, the proportion of explained variance, also has a column with the label R. And in this case, it has exactly the same value as the standardized coefficient. And that's no coincidence. They are the same by definition in a simple linear regression model where we just have one independent variable. Because the reason that R squared is called R squared is not coincidental, because R squared is basically nothing more in a simple linear regression model than the correlation coefficient squared. So the correlation coefficient multiplied by itself. You can check this for yourself. 0.235 times 0.235 works out to round about 0.055. So those are also directly related. So this R in R square is basically used as a letter to indicate the proportion of explained variance, because it is directly based on the R value, the R being used usually to indicate a correlation coefficient. Yeah, so in a simple linear regression model, those two, the R, the correlation coefficient and the standardized coefficient, and this R value you get in the model summary are exactly the same number, and R square is nothing more than this R value squared, because then we re-express it on the scale of variance. Yeah, correlation coefficient is on the scale of standard deviations. We want the R squared to be expressed on a scale of variance because it's supposed to reflect the explained variance. Well, how do we get from standard deviations to variances? Squaring, right? Because the standard deviation is taking the square root of the variance. So taking the standard deviation to the power of 2 gives you the variance. Taking the variance taking the square root of the variance gives you the standard deviation. So that's no coincidence whatsoever. So all of these different values are directly related, and in this case even exactly the same. So there is no fundamental difference between regression and correlation, just different scales that we are using. Which brings regression then, okay, correlation does not imply causation, but I also told you that multiple regression analysis is super popular because it allows us to make better causal inferences. So how does that work? Well, one of the reasons is that you can extend regression analysis, and you can extend it by including more than one independent or X variable in your model. So this is what we call multiple regression. And why is that important if we talk about causal effects? Well, if you're just looking at the bivariate association, so bivariate meaning referring to two variables, so bi for two and variate for variables, the bivariate association between X and Y, so that would be either a simple linear regression model or the correlation coefficient, again they are basically just the same expressed on different scales, is usually not a good representation of the actual causal effect of our independent variable on our dependent variable, because we usually work with observational data. So that means there's all kinds of other things that might have an impact on our dependent variable that might lead to a correlation between our independent and our dependent variable, or some kind of regression coefficient that tells us something about that relationship, but might not be just the consequence of, so the relationship that we find might not just be a consequence of the causal effect of our independent variable on our dependent variable. So, for instance, we might have these other variables that act as what we sometimes call confounders, confound the relationship. So there's, roughly speaking, two general situations that might be in place. So you might have a situation where there is some third variable, let's call that variable Z, that is in between X and Y. So we have a situation where our differences in our independent variable lead to differences in that Z variable, and differences in that Z variable lead to differences in our Y variable. Or on the right hand side, we might have a situation where we have a third variable, a Z variable, where we say differences in this third variable, this variable Z, lead to differences in X, and these differences in Z also lead to differences in Y in our dependent variable. So these are two subtly different situations. For now, we're going to focus on the situation depicted on the right hand side of this picture. So the situation where we say our third variable Z is a confounder because there is we expect it to have an effect on our independent variable, and we expect it to have an effect on our dependent variable. And then if we would just look at the correlation or the simple linear regression model of X and Y, then that would not be a good representation of the causal effect, because to some extent the relationship that we find is actually due to that third variable, that Z variable. Later in the course, we'll come back to the picture on the left-hand side, because there it can be a little bit more complicated as to whether or not there's actually a confounding relationship going on. But for now, focusing on the right-hand side of this picture. So we have x, our independent variable, y, our dependent variable, and z, this hypothetical third variable that might act as a confounder in that x-y relationship. So let's, for instance, assume that I want to test this hypothesis. The higher people's income is, the more satisfied they are with their government. This is one that we already tested before, right? So we can represent this in this nice conceptual model. So we put our independent variable on the left-hand side, we put our dependent variable on the right-hand side, and we draw an arrow from left to right, indicating that our hypothesis expects a causal effect. In this case, it's a positive effect, so I could put a little plus sign on top of that to be even clearer. But the arrow is running from left to right, so we are expecting, based on our theory, that it's actually a causal effect, that more income leads to more satisfaction. So they're not just correlated. Actually, it is really because of higher income values, we get higher satisfaction with government values. Okay, so we could do the simple linear regression model that we already did, or we could calculate the correlation coefficient. Is this now a good test of our theory, if this theory is a story about the causal effect of income on satisfaction with government? Well, there are reasons to expect that it may not be. So for instance, we might think, yeah, okay, so we have observed differences in income, we have to observe differences in satisfaction with government. But for instance, we know that income is also related to age. Specifically, as people get older, they tend to earn more income, right? I mean, most of you are still pretty young, and so most of you are, well, full-time students, maybe have a part-time job, but probably it's not the last job you will ever have. It's probably also not the job requiring the most highest level of education or skill or experience. So probably also because of that, you're not earning that much yet because you're young. So we know that this is generally the case. Younger people tend to earn less, so tend to have a lower income than older people. So we know that as people get older, they will start to earn more income. So age has an effect on income. Yeah, so we can draw a causal arrow running from age to income. It's also quite plausible to think that, yeah, age might also have an influence on satisfaction with government. Yeah, could think about all kinds of theories that say something about that. So for instance, you might think something like, yeah, well, all the generations are maybe a little bit better represented by the government. So maybe the government is, more in favor of policies that in particular favor the older people in the population and not so much the young people in the population. And so these people might be more satisfied with government if the policies are in line with what is good for them, are in their interest, basically. So that might be a reason to think that, maybe it is also the case that as people get older, they also become more satisfied with their governments. So in theory, what we have here is a hypothetical confounding variable, age, because we can think of theories that tell us that it's likely that age has an effect on income, and we can also think of theories that tell us that it's likely that age has an effect on satisfaction with government. As a matter of fact, if you go to the literature, you'll find that there's actually a lot of study that have been done, empirical studies that already show that, it's quite likely that there is as a relationship between age and income, and a relationship between satisfaction with government and age. So that's a strong indication that this is a potential confounding variable, age. So if we are only looking at the simple linear regression model, then the coefficient that we get isn't just based on the actual causal effect of income on satisfaction with government, but to some extent is also just a result of the fact that, for instance, more age leads to more income, and more age also leads to more satisfaction with government, so that there is this third variable that we haven't taken into account. So in other words, if we would now just estimate a simple linear regression model, so satisfaction with government for each case I is B0 plus B1 income plus an error term, then we might get a wrong estimate for the causal effect of income, because age is confounding the relationship. And of course, that's a bad situation, because if your hypothesis is based on a theory that says, well, this has to be a causal effect, then what we are now getting for our B1 coefficient is actually the wrong estimate, because it's not really an estimate of the true causal effect. And that might, of course, lead us to make a wrong conclusion about the hypothesis. Yeah, so we want to do better than that. We want to get closer to an estimate of the actual causal effect of income on satisfaction with government if we want to test our theories as stringently as possible. So how can we do that? Well, in this case, if we know that h is a confounding variable, well, we can include h in our regression model. So instead of one x variable, we now have two x variables. We have income, which we have a hypothesis about, but we have also included h as a variable. So we get a new coefficient, B2, a second coefficient in our regression model. And now we can estimate both of these coefficients together at the same time. Yeah, so in this case, what we are doing is we're saying, well, we have a hypothesis about the income effect, but we want to control or adjust for differences in h. We want to say something about the effect of income that we know is unrelated to differences in h, because we know h is a potential confounding variable. So this is basically why multiple regression is really, really useful if you want to make stronger claims about causal effects, because it allows you to do that. By including a variable in your model, you are controlling or adjusting for differences on that variable between your cases. Yeah. So that's basically the idea of multiple regression, whereas the multiple coming from we are estimating the effects of multiple x variables at the same time. Yeah, that's why it's called multiple regression. So in general, we will have a formula where we say, well, we still have our variable on the dependent variable y for each case I, that's equal to a constant value, b0, that's the same for everybody, plus b1 x1 now. Yeah, so now we're using numbers to indicate what x variable we are talking about, because we can now have multiple x variables. So we'll have our first coefficient b1 for our first independent variable, which can take different values for different cases. We have plus b2, our second coefficient for our second independent variable, which can take different values for different cases. And we could, well, add in a third variable or a fourth variable or a fifth variable, and so on and so forth. So we can just keep adding variables to that model, and for each new variable that we add to the model, we get a new coefficient. So k here stands for the total number of variables, x variables, that you want to include in your model. So that could be, in theory, any number, 10, 50, 100 in theory. Yeah, so we get coefficients for each independent variable in our multiple regression model. So that's the general formula. So what do these coefficients now represent? They represent the effects of that specific x variable on our dependent variable, controlled or adjusted for the effects of all the other x variables that we have included in the model. Yeah, so each one of those x variables, of these variables that we add in our model, might have some effect on our dependent variable. And the coefficients that we do get tell us, well, what is the effect in this case, for instance, for x1? Yeah, so for our first variable, so that would be the b1 coefficient. What is the effect of that controlling for the effects of x2 and x3, x4, yeah, depending on how many independent variables we have in our model. So basically it tells you what is the effect of x1 that does not depend on differences in x2, x3, and all the other independent variables in our model. So that's the idea of controlling. By including them in our model, we're basically making sure that the coefficients for the other independent variables that we include in the model are no longer, to some extent, the result of differences in those variables that we are including. Yeah. And the nice thing about these multiple regression models is we can just use OLS as a method of estimation. So we did this manually in the last B lecture for a small number of observations. We saw that the formula, although still a bit daunting, wasn't actually that complicated to solve. Well, we can use a variation of that same formula for multiple regression models, so to find the values of not just a B1 coefficient, but of a B1, B2, B3, all those different coefficients. The formulas then do become a little bit more complicated, so I'm not going to make you run through them manually because they involve things like matrix algebra, which might not be super familiar to most of you. But the basic idea is still the same. We're basically still using the OLS method to find the right values for our coefficients. Yeah. So in the example that we used, where we said, well, we can estimate the simple linear regression model for satisfaction of government as B0 plus B1 income plus some error term. And we did that in one of the last lectures. We found that the regression coefficient that we find for income is 0.167. Yeah, so for every decile of household income, more the predicted value on satisfaction of government increases by 0.167 points. And we saw that the associated p-value for that coefficient was very, very small. So it was a lot smaller than 0.001. So very, very unlikely to find this in our sample under the assumption that in the population income has no effect whatsoever on satisfaction with government. But, well, if you're trying to test a hypothesis that is based on a causal theory, yeah, so a theory that it's because of differences in income that we get more satisfaction with government, that's really a causal effect, then, well, if we just saw that h might be a potential confounding variable and we did not include that in this model, so the coefficient that we find of 0.167 might not be a great reflection of the actual causal effect of income. So once we know that, we also know how to solve the problem. Well, just estimate a new model and then not just include income as an independent variable, but also re-include h. So we're including also h as a variable in our model. So we get a second regression coefficient for that h variable. Very strictly speaking, we would say h in this case is a control variable because we don't have a hypothesis about h, but we want to use h as a control variable because we know that h is a potential confounder in the relationship between income and satisfaction with government. Very formally speaking, would say if we have a hypothesis about something, it's an independent variable. If you're just using it to control, then it's a control variable. Mathematically speaking, they are exactly identical. So it doesn't matter for your OLS estimated regression model. It doesn't matter for SPSS whether something is an independent variable or a control variable. It gives you exactly the same result. So this is really up to you as a researcher to think about. Yeah, but you can do this. In this case, I did this. And well, in this case, I found a new regression coefficient for income, which is a little bit different. I found the value of 0.166. So in this case, the difference between the simple linear regression model and the regression model where we have also controlled for differences in age, the multiple linear regression model is very, very, very small. So it's still more or less the same coefficient. The p-value is also quite small, again, in this new estimate. So not a lot changed, but at least now we know. Now at least we know what the effect is of income that is unrelated to differences in age that we included in our model. And it could be also a completely different result, so that the coefficient might have gotten a completely different value. The p-value might have increased a lot or decreased a lot. It might even been the case that all of a sudden our coefficient would have been negative, and maybe even negative with a super small p-value. So it could go in all directions, basically, and you only know once you include it in your model. So you only know once you actually check, and you check by including it in your multiple linear regression model. So what can we now say? Again, thankfully in this case we could say, well, our hypothesis that the higher people's income is, the more satisfied they are with government is still supported. But now we have a little bit of a better test, a more rigorous test, because we took into account that the initial effect of income that we found, so this 0.167, may have just been due to differences in age between the people that we have observed. So now we have excluded that problem. Yeah, so our test of the theory has improved a little bit. So how to interpret now this coefficient? Well, we still interpret them on the scales on which they are measured. So in this case, we could still say, well, for every 1 decile increase in household income, the predicted value on satisfaction with the government increases by 0.166 points. But in this case, holding the effect of age on satisfaction constant. Yeah, so we have to be aware that once we start including independent more variables in our model, more X variables in our model, then the interpretation of the effects also changes, because now we have to interpret these effects as this is the effect of this variable holding the effect of all the other variables that we included constant. So basically controlling for them or adjusting for them. All of these things are more or less equivalent in their meaning. Yeah, so holding effect of H on satisfaction with government constant. Yeah. Cool. Of course, we also have a second coefficient now in our model, so H, which we just said, well, we don't have a hypothesis about that, but it's just a control variable. But we will find a coefficient for that, so if you would want to interpret that, well, in this case, I found a negative coefficient for H, minus 0.002, and I found a p-value of 0.515. So we could say in this case, if you would have a hypothesis about the H effect, we might want to make a statement. Will want to make a statement about that hypothesis, and then we could treat income as a control variable. So in this case, we would interpret this coefficient B2 as well, controlling for the effect of income. We cannot, in this case, reject the null hypothesis that there's no effect of H on satisfaction with government, because we have a super high p-value. Yeah. So always remember, if you interpret these models, these coefficients, you have to also look at what else is in the model, because it changes the interpretation. Once we have more variable, we need to be aware that the interpretation is also as this is the effect for this variable, controlled for all the other variables that we put in our model. So how does this whole control business actually work? Why can we interpret this as holding the effect of the other variable constant, or controlling for the effect of that other variable, or adjusting for the effect of that other variable? Well, it basically works like this. In the last B lecture, I briefly touched on the idea that the way we estimate these regression coefficients in a simple linear regression model is basically we're looking at the covariance between X and Y. So how do differences in X go together with differences in Y, divided by the variance in our independent variable X. So basically the coefficients that we find are based on the covariance. So how do the differences in X go together with differences in Y? Well, when you have multiple regression models, then the estimates of all our coefficients, of our B coefficients, are based on the unique covariance of X and Y. So that part of the variance in our dependent variable that is not associated with the other independent variables, X variables, that we included in our model. So if we come back to our example, so this B1 coefficient for income, what is it based on? It is based on the covariance of income and satisfaction with government that is completely unrelated to the variance in H. So more simply put, those differences in income between people that we observe that go together with differences in satisfaction with government, but have absolutely nothing to do with differences in H. Yeah, that's basically the layman's interpretation of that. So basically it is looking at the covariance that we have between all our variables, and then just basing our regression coefficients on the unique bits of covariance that we find. So those differences in our independent variables that go together with differences in our dependent variable, but are completely unrelated to differences in all the other variables that we included in our model. So that's the idea of basing these estimates on the unique covariance of X and Y. That's basically the logic behind how that controlling actually works. So what do you get when you do this in SPSS? Well, again, you get a bunch of tables, of course. As always, the SPSS output will first give you these tables with variables entered and removed. And like we already saw, this gives you an overview of what is the model that you just estimated. In this case, well, we just have one model that we estimated. We included H, but now we also included income. And the nice thing is that SPSS will actually tell you that. So you now see that variables entered, that column tells you that H, so AGEA, H of respondent calculated, is included in the model, but also HINCTNTA, household income net, all sources, is included. So both of these variables are now included at the same time in our first model. So again, useful table if you're doing lots of models, because then you know exactly what variables were entered in this specific model. So variables entered really just means what X variables did you enter into your model. We'll get a model summary as we did before. We already discussed the interpretation of the R-square value in the simple linear regression model. And we now already also know what the relationship is between R and R square. Now we have a multiple regression model that also somewhat changes the interpretation of R square, because it is now still a proportion of explained variance in our dependent variable, but it is the proportion of variance explained by all the independent variables that we included in our model at the same time. So in this case, we included 2 variables in our model, income and age. So this R square value of 0.055 is the proportion of variance in satisfaction with government that is explained by differences in age and income. Both of them, yeah. So that's how to interpret this R square value, the proportion of variance in our dependent variable that is explained by, well, in this case, both of our X variables. And if we would have included more X variables, then whatever number of X variables we have included in our model. So it evaluates the explained variance in our dependent variable based on the entire model that we estimated. And now it also becomes a little bit more relevant to look at that column besides that, the so-called adjusted R square value, because that's a different measurement of R square, which also is supposed to represent a proportion of explained variance, but it does so adjusted for the number of independent variables in our model. The logic being that, by definition, if you include more independent variables, R square is always going to go up. And that also means that the R square values that you find in your sample might be a little bit higher on average than the population R square values, because just including more variables always means that you're somewhat pushing up that R square value, and that could be just due to the sample that you have happened to observe. So people thought about, well, how can we somehow compensate for the fact that if we just enter more X variables, then R square always goes up, because we want R square also to be at least somewhat a decent reflection of the of an estimate of the R square value that we would get in the population. And so the idea is that there is a formula to adjust your R square value in such a way that it is being brought down a little bit depending on how many independent variables you have in your model. So in this case, you see we have 2 independent variables. So there's a little bit of a difference between the adjusted R square and the original R square, because it is compensating for the fact that we now have 2 variables included. If we would have 10 variables included, that value would be even a little bit smaller. If we would have 20 variables included, that variable would be smaller still. So it's the idea that the more independent variables you put into your model, the more you want to compensate your R square value for the fact that it is by definition always going up, no matter how bad your independent variables are at actually explaining your outcome variable in the population. Now, I'm not going to spend too much time on that, because there are about 5 different formulas to adjust your R square values, and it isn't exactly clear which one of those would be the best. SPSS just picks one of those for you, but it is useful in the sense that if you want to have a rough idea of, well, what would be the most likely, my most likely guess of the explained variance if I were to be able to explain my dependent variable for the entire population with my independent variables, then it would be that adjusted R square value. That's the idea. So we still get an ANOVA table as well. We already saw what that table tells us and what it is based on, sum of squares of the model and the residual and the total, and then using those to calculate mean sum of squares, and from that we can get the F statistic, and from that we can get the p-value. All of that is basically still the same, but now the model is a little bit more complicated. But our F test still tests the same null hypothesis that it did before. So in the simple linear regression model, our F test in the ANOVA table tested the null hypothesis that R square is 0 in the population, so that our model explains no variance at all in the population, against the alternative hypothesis that it explains some variance in the population, so that R square is actually larger than 0. So in this case, what does that null hypothesis mean? Well, it's based on a model where we have 2 independent variables included, age and income. So what do we say when we say h0 r square is 0? We are saying that our null hypothesis is that differences in age and income explain jointly exactly no variation whatsoever in satisfaction with the national government in the population. So r square is 0. Yeah. Again, r square value in a multiple regression model is the proportion of explained variance based on all the variables that you included in your model. So that means that the null hypothesis about that r square value is going to be a null hypothesis that says something about, well, what could we assume about how much variation all of our independent variables would explain in the population. And again then if we can reject that null hypothesis, then that would favor that the alternative hypothesis that r square is larger than 0 is a positive value in the population. In other words, that differences in age and income jointly explain at least some of the variance in satisfaction with the national government. So in other words, we are testing whether our new fancy model with two independent variables, income and age, is a model that is significantly better fitting than, again, the most simple model that we can think of, the model where we're just using the mean value on satisfaction with government as a prediction. Yeah, remember from the linear regression model, that's basically what we are testing here, this model against the model with the independent variable included. Well, now we included more than one independent variable, but it's still comparing to this very, very simple baseline model of a model without any independent variables, so just a constant value, which is just a model for the mean of our dependent variable. So in other words, our f-test tests whether our new, more fancy, complicated model is significantly better fitting than our most simple model. Yeah, so in this case, we would say, well, our p-value is really, really, really low. It's 0.000 small. So in this case, we would say, well, it's very, very, very unlikely to find what we find here. If it is in fact true that differences in age and income explain no variation at all in satisfaction with the national government, in other words, it's very, very, very unlikely that we would find this if the model that includes differences in age and income to predict differences in satisfaction with government actually is no better at predicting differences in satisfaction with government than when we just use the mean value to predict differences in satisfaction with government. Yeah. So, just to talk a little bit more about this idea that what we're actually doing here implicitly is comparing models, because that's going to become super useful in the remainder of the course. So I'm already getting a little bit of a start on generalizing that idea. So in this case, notice that what are we doing? We are comparing basically two models. The model where we're just using the mean as a prediction. So that's the simple model up here. B0 reflects the mean on satisfaction with government plus our error term, which then just the deviation score. And we have the more complicated model where we have a coefficient for income and a coefficient for age that we're also estimating. But if you compare these two models, a lot of those two models is the same. We have the same dependent variable, we have a constant that's the same, and we have an error term that's the same. So the only thing that's really different between this model, the simple model, and the more complicated model down here is that we included B1 income and B2 age. Or if we start from the perspective of looking at this model, we could say, well, we can get from this model to this more simple model by taking out B1 times income and B2 times age. If you just remove those two parts of the model, then we are left with this more simple model, which is basically the same thing as saying that if we would assume B1 to be of the value 0 and B2 to be of the value 0, because again, if we multiply something by 0 in the equation, then it becomes 0, whatever is coming out, and we can just drop it from the equation. So taking this out is the same thing as saying B1 has to be 0, and taking H out is the same thing as saying B2 has to be 0. Yeah, basically what we're doing is we are forcing our B1 and our B2 coefficients to take the value 0 if we have this model, because then these two things drop out from our equation. Yeah, so we have a situation where we have a complicated model and we have a simple model, and we can get from the more complicated model to the simple model simply by removing things from the more complicated model, or in other words, assuming that they are 0. In this case, income, the coefficient for income and age. So in general, we will often have models where we say we have a more complicated potential model and a more simple potential model, but the models are otherwise exactly the same. It's just one is a more complicated version of the other model. So whenever we have the situation where we have a more simple statistical model and a more complicated model, and we can get from the complicated model to the simpler model simply by taking things out, removing elements from our complicated model so we get a simpler model. So removing coefficients and the corresponding independent variables from our model, then we call those models nested. They are nested within each other. So in this case, you could say the model that we have up here, so just taking B0, the mean value of satisfaction with government, is nested in this more general complicated model. Because this is just a simpler version of this, where we have forced B1 and B2 to take the value 0. So in general, we will have often a situation where we have different potential models, where we could say our simpler models are actually nested within our more complicated models. And that's actually often super useful, because that means we can systematically compare different models that are nested within each other in terms of how well they fit the data. Because now we're talking about multiple regression models. That means, in theory, we could have any number of X variables in our model. So it becomes more important now to decide on, what X variables to include. And one of the ways we might go about doing that is by looking at the goodness of fit of different models. And then it's useful to know whether the models are nested, because that we can then use to actually statistically test if some model is that's more complicated is really actually also better fitting with the data than a more simple but nested version of that same model. So last week we saw that we can use the F-test to compare a model with one independent variable to a model with no independent variables. And we have already now seen that the same F-test, if you have a multiple regression model, compares whatever model we have estimated with how many independent variables we have included, again, to the most simple model with no independent variables. And we saw that there are two ways of calculating that F value that are the same, mathematically exactly the same. It's just a little bit easier probably to interpret this version of the F-test statistic formula than this one, but they are exactly identical in terms of what the result would be. This formula actually can be extended with a few tweaks in such a way that we can use it to test any set of nested models against each other, so that we can start to not just look, did the R-square value increase, but that we can actually formally do statistical hypothesis tests to see, we have a more complicated model, we have a simpler model, does the more complicated model actually fit so much better that we can also maybe say, this is statistically significant, if you want to use those terms. So that's going to be super useful in the remainder of this course, because we will see that later on we are going to look at theoretical hypotheses that are really interesting, but that require us to use this knowledge. So why would you want to tweak this formula in such a way that you could do that? Because of this. You have more independent variables in your model. R-square always increases. The question is really, does it increase by so much that we'll say, this more complicated model is really, really, significantly better fitting than our more simple model. So that's why you might want to do that. How does it work? This is how you can extend that that value, that formula for the F-test statistic. Again, it looks a bit the same. So I'm basing this on an extension of the second way we saw of writing the formula for the F statistic. So we have n minus k nu minus 1 times r square change divided by k change times 1 minus r square nu. A couple of things we know already what they are. We know that n is just a sample size over here. So n is sample size. K usually has something to do with the number of independent variables in your model. R square we know is the proportion of explained variance, but now we just have, we have new, here we have change, we have new. So what does that mean? Let's walk through that step by step. When we're talking about k new, k stands for number of x variables. And if we're talking about new, we're talking about the new, more complicated model. So you have to think about this from the logic of we start with a simple model, and then step by step we make the models more complicated. So we have a new model that's a more complicated version of a model that we started out with. So in this course we started out with a model where we just have differences in income explain differences in satisfaction with government, and now we have in this lecture made a new model where we say no, we're also including differences in age as an x variable. So we have our new model with now two x variables included. So k new stands for the number of variables in our new, more complicated model. Whereas k change stands for the difference in the number of x variables between our new model and our old model, our more simple model. So how many extra x variables do we have in the new model? So by how much did this number k of x variables change, go up from the simple model to the more complicated model? So in our case, we added just one extra independent variable, age. So in this case, the value for k change would be 1. But we could also have added, age, gender, socioeconomic status, all kinds of other variables to our model. Let's assume that we would have included gender and socioeconomic status. Then k change would have been 2, because we have added 2 variables to our simple model. So number of new x variables, that is what this k change refers to. Then also, what is r squared change? Then it's how much more variance we are explaining with our new, more complicated model compared to the simpler old model. Yeah, so if our first simple model, for instance, would explain have an r square of 0.2, so 20% explained variance, and our new model would have an r square value of 0.3. So 30% of explained variance, then r squared change would be 0.1, the difference between them. So how much did r square go up in our more complicated new model compared to our simple model? And then the r square new again refers to the proportion of explained variance in our new, more complicated model. So in our new model, where we have all the complexity, all the x variables included, what is the r square value? What is the proportion of variance that is explained by all our variables in our more complicated model? So that's basically how to interpret different elements of that formula. But that we can then use to, compare any set of 2 nested models. So we can compare a model with 3 independent variables to a model with 10 independent variables and see, is the goodness of fit significantly better? So did r square go up by so much that we can reject the null hypothesis that our more complicated model actually isn't any better in predicting our dependent variable than the simple model that we had in the population. So what we are doing then with this test is we are testing again a null hypothesis about r square, and what we are formally testing is the null hypothesis that r square change is 0 in the population against the alternative hypothesis that it is larger than 0 and it's a positive value. So in other words, the null hypothesis in this case being we have a new, more complicated model. We start with the assumption that if we would have estimated this model based on the entire population, and we would have compared that to the more simple model that we could have estimated based on the entire population, then there would be no difference at all in the proportion of explained variance. So the more complicated model wouldn't be any better in explaining variation in our dependent variable than a simple model. Of course, again, then if you can reject that null hypothesis, so if you find a small p-value for your f-test, then that offers support for the alternative hypothesis that actually r square change is positive, so that the hypothesis that in the population adding these new variables, so making our model more complicated, actually means that we are able to explain more variance in our dependent variable. So that would be the formal test that we could do. I'm going to leave it at that for now. You won't need to worry about this more extended f-test in the coming assignment, but after that it will become something you have to work with. So for now I'm going to just go over to what is probably the most interesting bit. So we have our multiple regression model, we get our coefficients table with all the individual regression coefficients that we estimated and the standard errors that go along with those, which looks like the coefficients table that we already saw. So we have the same unstandardized and standardized coefficients, t-values and p-values, but now we have more than one independent variable. So we have income and we have age. As you can see here, we have income, HINCT, and the age variable that we both included at the same time in our model. So how do we find the right values? Well, our B0, our constant value, is, well, just the first coefficient that's listed after constant. So B0 is that value that we get after the unstandardized coefficient for the constant. Our B1 coefficient, in this case for x1, which was our income variable, that was our first x variable, is going to be the one that is listed after that specific variable. So in this case, it's the second unstandardized coefficient we get in the table. And lo and behold, for the second coefficient that we have for our h variable, that's going to be the second coefficient in our table, as you can see here, because this is the row that belongs to the h variable. Right, so now we have a multiple linear regression model that tells us about a constant value, B0, that tells us about a regression coefficient for income, a B1, which is the effect of income controlled for difference in age, and we get a regression coefficient B2 for the effect of age, which is the coefficient for the effect of age controlled for differences in income. So in other words, how would we interpret these three coefficients B0, B1, and B2? Well, B0, well, what is the constant value? The constant value is the predicted value based on our model when all our independent variables take the value 0. Yeah, remember, if something takes the value 0, then we multiply by 0, and then we can just drop it from the equation. So what is B0? What is the interpretation of our constant B0? It is that predicted value if B1 would be multiplied by 0 and B2 would be multiplied by 0. In other words, it is that predicted value when income and age take the value 0. So in other words, for a person that earns 0 income and is 0 years old, the predicted value on satisfaction of the national government is 4.168 points. Again, that makes no sense because such a person doesn't exist, but that doesn't need to worry us for now. But it is the interpretation of the constant. So that's the predicted value if all our independent variables are at their 0 value. So for a person with income 0 and age 0, the predicted value is 4.168 points on satisfaction of the national government. And then we can say, well, for every additional decile of household income, that predicted value increases by 0.166 points, holding the effect of age on satisfaction of the national government constant. Yeah, again, we are interpreting these coefficients by recognizing that we have also included now a second variable, so we need to include that in our interpretation. Yeah, and so vice versa. How would we interpret the coefficient that we find for age of minus 0.002? Well, for every year older a person is, the predicted value on satisfaction of the national government decreases by 0.002 points, holding the effect of income on satisfaction with the national government constant. Yeah, so that is the idea that what we have here is an age effect that we know has nothing to do with the differences in income that we have observed. And we have an income effect that we know has nothing to do with the difference in age that we were able to observe in our data set. So again, this means that we can interpret these as controlled estimates of the effect. Yeah, so that's basically where you can find these different values. So it's not really that much more complicated. As the simple linear regression model, we are just adding more x variables to our model, so we get more coefficients in our table. Now, as I said, well, this is a very simple example. We just have 2 x variables, but we could include as many as we want to. In theory, so if you say, well, there's 400 independent or X variables in my European social survey data set, I'm just going to include all of them. You could, nobody's stopping you, but in practice, I wouldn't recommend it. In practice, we have to be very parsimonious. It's a fancy word of saying not making it more complicated than it needs to be. And for good reason. Because, making your models more complicated than they need to be can be a bit dangerous. So basically, there's, roughly speaking, two things we need to take into account. One is that we really have to think about our sample size and be aware of the risk of overfitting our data. And the other, and that is a somewhat related problem, is that we have to be aware of potential problems with multi-collinearity. Great Scrabble word. Something that I will explain both of these issues a little bit to you now, and later in the course we'll get a little bit deeper into them. But it's good if you already have some kind of familiarity with them. So the number of X variables that we really can include is really limited by these two factors, basically the sample size and the potential for multi-collinearity. So if you're talking about sample size, well, we're doing statistical research, so more is always better. Because more variation, more cases, more observations means that we have more information, and the more information we have, the better our statistics work, the more reliable they become, basically, right? So maybe you still are very much in the mindset of qualitative case study research, where you often have to really be careful about, well, what case am I going to include? And that is because you can only include a few cases, because that's qualitative research means that you really have to focus on those specific cases. So you have to be very careful in thinking about, well, what cases can I include from a theoretical perspective, which makes what makes the most sense. The reasoning in statistical research is really the other way around. Include whatever you can include, as long as it makes sense theoretically. So if the cases that you observe are good measurements, and they are cases which your theory is supposed to say something about, so to which your theory is supposed to generalize, then do include them, because more is better. Larger sample size means more variation. More variation means that we have more information. The more information we have, the better our statistics become. So more specifically, well, you already know that our point estimates, so our estimates for means, or in our case now regression coefficients, become more reliable as a measure of the true population parameters to which we actually want them to refer, the larger our sample size is. And we already discussed this quite a bit, the idea that of an hypothetical sampling distribution and what we know about the shape of that sampling distribution based on the central limit theorem. And we know that the sampling distribution is going to become smaller, narrower, the larger our sample size is. Yeah, so the larger our sample size is, the less spread out all potential hypothetical sample estimates are going to be around our true population parameter, which also means that for each individual sample, the probability of that specific sample estimate being close to the population parameter increase, because they are not so spread out. So there's not so much noise going on in our estimates. So the larger our sample size is, the more reliable our coefficients are going to become. Yeah, and that also implies that the larger our sample is, the more statistical power we have. And statistical power basically means that that refers to, well, our ability to actually find an effect that actually exists in the population. Yeah, so we only observe a sample, and we do not want to find effects in our sample and say that they are true effects if there is no effect in the population. But at the same time, we also do want our sample to show us that there are effects if there are in fact effects in the population. So basically, the larger our sample is, the more likely it is that we do find the effects in our sample that are actually there in the population. So larger sample means more statistical power. Basically, finding smaller p-values, and so having a bigger chance of rejecting your null hypothesis when you actually should be rejecting your null hypothesis, because there really is an effect in the population. Yeah, so that's the idea of statistical power. And more observation just means more statistical power. Remember when we talked about the standard error, that I showed you that as the sample size goes up, the value of the standard error goes down, keeping all else equal. And what does that mean if you have a smaller standard error? Well, it means that we have more precision, that our estimates, our coefficients are more reliable. And of course, it also means that our t-value is going to go up, because smaller standard error means larger t-value, because what is the t-value? It's the coefficient divided by the standard error. If we're dividing by a smaller number, we get a larger number. We get a larger t-value. A larger t-value means smaller p-value. So more sample size, more statistical power. There's also another issue. The more independent variables you include in your model, the more coefficients you're trying to estimate. So the more b coefficients are in your model that you need to find a value for. But finding the right value, so estimating these coefficients reliably, requires information. So you need to have variation, you need samples, sample size, you need observations. So if you have too many independent variables, well, you don't have enough information to actually estimate them, you might get very unreliable estimates. It might even be the case that you start to get really bad estimates because you're basically asking more from your data in terms of coefficients than there is actually information in the data. And that can lead to a case of overfitting, where basically the values that you find for the coefficients aren't generalizable at all to the population anymore, but are just basically reflecting the sample that you have happened to observe with all the idiosyncratic properties of that sample. Yeah, so that's at the risk of overfitting. So you want to have enough independent variables to get the right estimates, but you don't want to have so many that we are basically requiring more information than the data has for you, because then you can get into that situation where you're just overfitting your data. And again, later in the course, we'll see some specific examples of overfitting, adding too many b coefficients to your model, and why it can lead to really terrible results in specific situations. But for now, it's just good to be aware of this issue, that don't just dump all your independent variables in your model and hope for the best, but be aware that it doesn't necessarily improve the quality of your model, and dumping in too many independent variables can actually make it worse rather than better. Yeah, so that's one thing to take into account. Of course, you want me to give you a number, and my answer would be, well, it depends. How much is enough? How much sample size do you need? And it really does depend. It depends on lots of different things. It depends on the variances of your variables that you observe. It depends on the actual size of the effects in the population that you're trying to estimate. So it depends on a lot of different things. It depends on how many independent variables you want to estimate at the same time, and also a couple of other issues. Way too complicated and too much to go into now. Also often things that aren't answerable at all, at least not in the sense that we can just check the data for answers. We can only theoretically answer these questions. But of course, you want to have some kind of guideline. So I'm giving you a rule of thumb with the understanding that it's really just that, a rule of thumb. So that doesn't mean that this is set in stone, that you have to follow this rule to the letter, that it always will give you good results. It won't. Or that that you might not sometimes have okay results if you don't follow this rule. Sometimes you might. But it's really just a rule of thumb. And so a somewhat, let's say, useful one is try to have at least 50 cases. Again, this is rule of thumb, so there's no fundamental difference between 51 and 49 or anything like that, but it's just, try to have at least 50, because then at least we have a somewhat reliable estimate of a mean, and maybe even a conditional mean, which is what regression model really is. And then for each independent variable that you have, try to have at least 5 to 10 cases. More is better. Yeah, so the more independent variables you have, the more cases you need to reliably estimate them. So I would say if you have if you have 10 independent variables that you, x variables that you want to analyze, that means you should really aim for at least 100 observations if you want to be somewhat safe. And even then, it's still, this is like an absolute minimum. More is better. So if you can include more, please do include more, because it's only going to make the statistics better. Now, one last thing to talk about multicollinearity. You might, I just talked about how control in a multiple regression model works by basing our estimates of the coefficients for each x variable on the unique covariance between our x variable and our y variable. So that part of the variance of the differences in our independent variable that go together with differences in our dependent variable, that is not also shared with differences in the other variables that we included in our model. But of course, that means that we have to have enough unique covariance. So in our case, in the model that we just estimated, there needs to be a sufficient, let's say, amount of variation going on in income, so differences in income that are associated with differences in satisfaction with government, but are completely unassociated with differences in age. And vice versa for the age variable, you also need a sufficient amount of unique covariance between age and satisfaction with government. So differences in age that are associated with differences in satisfaction with government, but have nothing to do with differences in income. So these pockets of unique covariance, if you want to think of them that way, need to be large enough to get a reliable estimate. And that might not always be the case. So it might be that the amount of unique covariance that you have between x and y, once you include more variables, becomes very, very, very small. And if that becomes very, very small, it means that there isn't a lot of information that we are basing these coefficient estimates on. And that is what multicollinearity is. It is what happens if you have a combination of x variables that really largely explain exactly the same part of the variance in your dependent variables. So it's exactly the same differences, or at least in part the same differences that both of those variables are associated with. So for instance, in our example, let's make it very, very extreme. So hypothetically speaking, let's say that all the differences in income that are associated with differences in satisfaction with government are also associated with differences in age. Then there is no unique covariance between age and income. So we have a situation of what we call perfect multicollinearity. So then there is nothing to reliably base your estimate of the regression coefficient for income on, because all of the differences in income that go together with difference in satisfaction of government also go together with differences in age. So that's the issue of multicollinearity. Or to pick an example where it's where we will have obviously multicollinearity to a very high degree. Let's suppose that you want to include age as an x variable in your model. So you measured age in years. So in years, how old is each of your respondents? And you also want to include birth year as an independent variable. So in what year was a person born? Well, theoretically you could do that, but of course, birth year and age, it's basically the same variable, just measured on a different scale. So for every additional year older that the person is, the birth year is going to be exactly 1 year earlier. So every difference in age is perfectly aligned with every difference in birth year, just expressed on a different scale. So those variables, age and birth year, would be perfectly correlated, which also means that there is no way that we can look at those differences in age that are associated with differences in satisfaction with government in this case, that have nothing to do with differences in birth year, because all the differences in age by definition go together always with differences in birth year. So in other words, when do you find multicollinearity issues? Well, it's usually the case when your x variables are already themselves very highly correlated. So the higher the correlation is between your x variables that you're trying to at the same time put into your model, the more of a risk you run of running into these problems of multicollinearity. Later in the course, we'll see some more fancy ways of trying to find out to what extent it is a problem, this multicollinearity issue. But the basic logic is basically that we need to be aware of how much overlap there is between the different X variables we put in our model. And why do we need to be aware of this? Well, if you have multicollinearity, that means that we don't have a lot of, maybe even no information at all to base our coefficient estimates on, which means they are going to be very, very imprecise. In other words, our standard errors are going to become large. We are going to get large standard errors, indicating that our coefficients are really, really not trustworthy, that there's really, really a lot of noise in our estimates, so they might be very, very, very far removed from the true population coefficients that we want to say something about. So when you have this issue of multicollinearity, and again later in the course you will see how to better find out whether it's an issue, you need to somehow either correct it or sometimes even the best case is just to prevent it. And preventing it basically means, well, don't put those variables into the same model at the same time, because it doesn't work. Again, there later we'll see that there are other ways of dealing with these issues, but for now it's good to at least have some kind of basic idea about that already. So that's multicollinearity. That was it for this one. Go work on the assignment, have fun with it, or maybe don't have fun with it, or at least don't get too frustrated. Come to the lab sessions if you need help, or help each other out on a Slack or discussion forum. And well, if you are board, there's going to be a bonus assignment as always, and also of course a B lecture that you can watch sometime before the start of next week. Good luck.